Good afternoon, everybody. It's my pleasure to participate in the 13th International Conference in Information Technology and Electrical Engineering, Chiang Mai, Thailand, 2021. The topic about artificial bee colony control of continuous stirred tank reactor in two stable steady states. My name is Al-Mohammedi, PhD candidate in electrical engineering with a major in digital signal processing and minor in telecommunication. My colleague, Dr. Fouad Alsunni, professor from system engineering at King Fahd University of Petroleum and Minerals, Dammam, Saudi Arabia. Outline, we start to introducing the Castor model. Then what's the problem statements? Our main contribution here. Then we list some literature, do some analysis of steady state and dynamic. Adaptive filter is the previous work called the recursive least square control. We propose heuristic method here called artificial bee colony control. The model on the right has two tanks. One they call the reactor in green, the other we call it cooling system. So the reactor has a volume V, concentration Ca, and temperature T. The inlet is a Q, which is the flow. Then concentration Ca naught and initial temperature T naught. And the output is a Q with the concentration Ca and temperature T. So the cooling system has a flow in the blue as the inlet and output referred as QC. So that this system has two differential equations, or represented by two differential equations. The first one, temperature. The other differential equation is force concentration. This model is a continuous stirred tank reactor, short for Castor. Here, some parameters. V is reactance, it's 100 liter. We have a temperature of reactants, we call T naught, for a cooling T C naught. So problem statement, RLS controller does not allow wide range selection of probe placement. It cannot exceed 0.08. So if you must 0.08, the method will not converge. Also, the estimate is not exactly, parameter estimate. Our contribution to propose a heuristic method called ABC controller. It can go up to 6.8 using pool placement method. And the parameter estimation is much better. Related work, external linear model, short for LM, has been proposed to approximate the linear system Castor model with adaptive control such as RLS in 3. Steady state and dynamic behavior was analyzed using ring cutters method in 4. This model is continuous. We have to discretize it. We are in digital world, so we use a delta model as proposed in 5. The RLS model using exponential forgetting factor was proposed in 6. Polynomial method with a pool placement has been proposed for signal tracking in 7. It's allow only nano range of pool placement. ABC algorithm has been successfully implemented for parameter estimation in wireless sensor network, WSN. In this work, we extend this, we will make ABC for Castor model. So steady state analysis. In steady state, reacting heats QR and cooling heat QC are equal using the previous differential equation. So the concentration Ca equal this equation. So we will plot stability point because we have to design it at S1 or S2, the stable points, because this model is nonlinear. So if we plot the QR in black and the QC, they are equal at S1. What is the temperature? Is 354. At some QR and QC, we use the previous equation. It will give concentration Ca equal 0.962. And S2. In this work, we will design it at S2 because it's more stable, as we will show. N1 is not stable point. So dynamic analysis, we have two outputs, Y1 and Y2. Remember, we have temperature and concentration. Input is the flow, which is QC. We will plot the input for minus 80%, which is referred at 60 liter per minutes inverse, and minus 60%, minus 40 up to 60. So time response of output to stable point S1 is this one. We can notice it's going to go from -1 up to 6 as we vary the inputs. While the other one, it will go from -20 up to 80. So we have a wide range of outputs. That's why we see that point S2 is much better. It has a wide range of variation. So adaptive control we'll design now. First, external linear model LM has an input output UT and YT. UT is the QC, is the flow, and the output is concentration. The second order transfer equation, transfer function, output by input. So the output will be second order and the input is the first order. Notice that the denominator has more order than the input, so it's rational. So this transfer function is continuous. We are in digital world. We have to discretize it. That's why we use a delta model. What is delta model? Gamma equals z minus 1. Z from signal and system course for discrete, and TV is a constant like 0.1, the sampling time. So the continuous time output, the second order equation, as we said, with unknown variables, which is A1, A0, B1, and B0. So we repeat the continuous output. We let t equal k minus 2, so remove every t, make it k minus 1, and so on. We use this relation. N derivatives equal gamma n. So for n equal 2, we make it gamma 2, and n equal 1, we make it gamma. Here there is no derivative, so nothing to do here, and so on. So last expression is this. Delta model is, we said, is gamma equals z minus 1. If we square it, so z minus 1 squared, we have z2 minus 2z plus 1. If we extend gamma y k minus 1 here, so what is gamma? We put a gamma here, z minus 1 times y k minus 2. So z y k minus 2 from signal and system course, it become y k minus 1. And this is nothing to happen here. So the last expression, we call it discretize y k minus 1. And we do similar thing. For instance, gamma square y k minus 2. What is gamma square? We have it here. We plug it here. So z square y k minus 2. Again, it will become yk, and so on. We call this one discretized yk. And this is a discretized equation using delta model. So the data vector and parameter, this is the data vector here, and this is the parameter. We need, this is they call unknown parameter, A1, A0, B1, B0, from what they call second order transfer function. And this is the discretized output. So we have a parameter times the data vector. If we use adaptive filter, this is the method, is well known from adaptive filter course. What's the main equation? Is this one. We have a delta, which is the vector to be estimated, and this is the data vector. So data vector, parameter vector. This one well-known equation for RLS method. So how we proceed for control structure? We have a QS and a transfer function. So QS here, forward transfer function, is this relation. If we use a Diophantine equation, it becomes, this is the desired signal. A from transfer function and B from transfer function parameters. And we have another equation. We call it feedback bool placement, and this is the method. Remember, alpha is the bool placement method from control course. So W is the track, is the signal we need to track it, and this Y is the tracked signal. We have some error, and remember this one continuous. So we have two states. The second order differential equation of the cluster will be differentiated with respect to T and CA for the input and the output. And this one would represent to input QC. So if we do that, we have the state space representation with the A matrix and B vector, and also C vector. So the cluster state space is this one here. If you use a MATLAB code, which is SS state space to transfer function, SS to TF, it will give this transfer function. So the first desired polynomial is this one. The second desired polynomial is this one. So from where we have two equations, remember? This is the first one and this is the second one. So if we proceed, we will solve now B naught plus A1 equal to alpha plus N1 and so on. And this terms here equal this term, and this term equal this one. If we solve for P naught, N naught, N1, Q, and so on, we have this is the solution. This is the simulation of RLS control simulation. We designed for two bool placement here, alpha equal 0.1 and lower bool placement is 0.09. We notice this one A naught estimate, and this one is A1, A naught A1 and B naught. And this is the signal, is a square shape signal W, and the output Y is good. I mean, this one for small bool placement and this one for higher bool placement. We overshoot here, and this one some delay. Now if we use the proposed method of ABC heuristic method, the input block signal is this one. Remember, this is the data, and this is optimum parameters we need to be estimate and known parameters. The desired signal is the multiplication of U and W. And this is the cost function. We need to minimize this cost function in order to have good estimate. Step 1, initialize the population of solution X as the following. So this is the row vector. It's 1 times M. And this one, each population, it has a column here. So this is the row, each one row, and this is the matrix X of T. So what is CS is the colony size. Half of it we call employee bees, and the other half is called scoot bees. So I equal 1 up to CS by 2 minus 1 employees bees, and M is what they call unknown filter, which is the vector of unknown estimate. Step 2, we solve for the objective function. Now we start recursive here. Step 3, T equal 1, then we proceed. So every time we repeat T4 up to so on, and we come back to step 4. So step 4, we produce a new solution called food source position Vijt in the neighborhood of Xij. So we have Xij, we plug it here, we will have another, we have Vij. So this one is random generated number from -1 up to 1. And we proceed. But remember, I not equal j here. Then we evaluate the new source position according to the objective function. Step 5, we use a greedy selection process between x and v. Step 6, calculate the probability value bt for the solution x of t. So we have to calculate probability. What is fit here? It's the cost function, 1 by 1 plus the cost function. It should be a positive number. Then step 7, produce the new solution, Vij, for the onlooker b's from the solution xit, which are selected depending on probability, and we evaluate the objective function. Then we apply greedy selection between xi and ve. Step 9, determine the abandoned solution. I mean, solution is not benefit. We have to discard it based on this relation as we did before. Here it's randomly generated number from -1 up to 1. Max and minimum is the boundary, upper and lower boundaries. Step 10, memorize the best swarm food source position achieved so far. So if the cost function is less than the previous optimum best swarm food solution, we will memorize it. Otherwise, we continue with the previous solution. Step 9, memorize the local best swarm food source position. If G minimum is lower than what they call, if J minimum is lower than the local best swarm, the previous iteration, we will memorize it. Otherwise, we will continue with the previous solution. Then we do recursively these steps unless we reach the maximum cycle number. We exit the method. This is a simulation of ABC. We use two pool placement. One is high, is a 3.2. The other one is 0.9. 3.2 give a best solution. Again here, this one for 0.9, it's not overshoot, but for 3.2 it's overshoot. So this one signal tracking parameter. In conclusion, we have discussed the development of a new heuristic method for parameter estimation called ABC. We saw it's perfectly tracked the reference signal with excellent parameter estimation. And this work, we can do ball placement up to 6.8, which is higher than previous work. Any question? I wish you have a nice weekend, inshallah.